Hi, hello, and welcome to the Study Podcast with Shivansh and Shiransh. Today we're talking about the dark stars in the James Webb Telescope.
So the James Webb Telescope is one of our main ways to try to look for these dark stars because it has both an infrared sensor and ultrasonic sensor.
So basically, before the James Webb Telescope's infrared capabilities, scientists were basically out of reach to discover the dark stars. But technically these are hypothetical celestial objects which are not powered by nuclear fusion, but dark matter annihilation, which talks about the process where dark matter collides with its own antimatter, resulting in both of them being destroyed and releasing a massive amount of energy and other particles.
So this is related to Hawking radiation, which we see in black holes.
And black holes are one of the strongest gravitational objects. They have one of the strongest gravitational pull because they're dead stars, and yeah.
So dark stars would basically be a lot cooler, larger, more diffused, and they would be, like the name suggests, dark for visible light, but in infrared they would be really bright.
So basically, unlike regular stars, dark stars are powered by annihilation of dark matter, specifically the weakly interactive massive particles, which are also known as WIMP, and also in the high density core of the early dark matter halos, WIMPs or WIMPs could collide and annihilate, which results in the massive amount of energy which I talked about before. As a result, these stars would also be cooler, and the surface temperature would be around 10,000 Kelvin versus millions of Kelvin for typical stars, which is a huge difference, 10,000 versus millions. They'd also be larger, which is around 10 astronomical units, and an astronomical unit is the distance from the Earth to the Sun, I believe.
Yes.
And they're also more diffuse than normal stars, and they're also more luminous, more visible through infrared rays.
Yeah.
And yeah.
So like we said earlier, the JWST is one of the most important tools we have for trying to look for these stars. So the reasons that the JWST is so good is because it has both an infrared sensor and an ultraviolet sensor. So we could use infrared vision to view the dark star in the first place, and we could compare that with some of the other released infrared from galaxies and other places. And we could compare that to rule out any other galaxies, and so far the James Webb Telescope has narrowed it down to 3.
The James Webb Telescope also has an MIR, I'll speak for the medical instrument, the mid-infrared instrument, which are made for observing the redshift objects.
So redshift is when galaxies, stars, anything like that is moving away from us, so their wavelength increases, making it more reddish, and this can increase to another level outside of visible rays when it's that much.
So when the wavelength of the radiation is increased, that basically corresponds to the decrease in the frequency and the photon energy. And photons are basically just particles of light, which causes the redshift.
Yes. So the JWST sensitivity and resolution are really good, so that we can actually look for these dark stars in really far spots. So we're thinking that these were formed 200 million years after the Big Bang. So that's really far away from us right now, which is why we need JWST's capabilities so that we can see that far away.
So basically why we say it's 400 million years after the Big Bang is because of light. When we observe something super far away, it takes time to travel here, and it takes that time, and technically they're behind us or ahead of us by the time that the light actually comes and gets sensed by our telescopes.
Yeah. So like we said earlier, so you need to focus on 3 main things that differ from regular stars to these dark stars. They're extremely bright in infrared, right? So we have to look out for that, which is one of the key things. The second most important thing is how there's not a lot of footprint in the ultraviolet rays, which many stars provide still.
So some of the challenges in detecting a dark star is the extremely bright in infrared but lacking the strong ultraviolet emissions, which is basically a trait of fusion-based stars, which we don't have in dark stars because they release gas and more particles. They're also bigger in size, like I said before, and they also exhibit a non-thermal spectral energy distribution, or SED. But these dark stars could also be confused with.
So they could be confused with high redshift galaxies, which basically means these are galaxies that are moving really fast, far away, really fast. And they could be confused with starburst regions, because like when the nova happens, they release energy in basically every single form of radiation you can think of. So this is why we need to look out for the ultraviolet areas, because we could confuse it with starbursts.
Exactly. So basically, in recent developments of the JWST, in 2023, researchers including Cosmin Life and Catherine Fies proposed that 3 candidate objects detected by the JWST could potentially be dark stars. And connecting back to before, dark stars are theoretical until now. And these candidates observed by the JWST Advanced Deep Extragalactic Survey, or JADES, displayed brightness and spectral features inconsistent with ordinary galaxies, which basically means they're different to normal stars, and showing properties of dark stars, which is very promising.
And also, their temperatures is really different, because the JWST is also able to see temperatures like a thermal camera. So if we're able to look at those stars, you'll see that they have a lot less temperature, like we stated earlier, 10,000 Kelvin versus millions, right? Mm-hmm. So the JWST will be able to figure those out, and that will make it a lot more clear. So that's how they've narrowed it down to 3.
So basically, these implications for cosmology and dark matter physics, it basically allows us to show if dark stars exist and are detected. The same thing with black holes before, when Stephen Hawking was still working on them. And their existence would imply that dark matter itself interacts with itself and not with other types of things. It also plays a direct role in baryonic structure formation,
which is the structure of the universe being created based on small particles, which can be negative or positive, because dark matter is negative matter.
And the dark matter's influence also extends beyond the gravitational effects, just like how black holes work. And yeah.
So the JWST is one of the most important tools in trying to find out dark stars, which is why we need to pay a lot of attention and try to look around in areas. Because even if we're looking at just a part of the night sky, it's so deep that we could probably find one dark star if we just search.
And that's it for our episode today. Thank you for joining us. This is Shreyansh and this is Shiv.
And we'll see you in the next one.
Yeah.